Hi, I'm Bill Kinney, and this is my fourth video about doing real analysis proofs. It's my second video about inequalities, fundamental inequalities part 2. There's three things I want to do, parts A, B, and C. I want to use induction, first of all, to prove that if x is bigger than -1, then 1 plus x to the n power is greater than or equal to 1 plus n times x for all natural numbers n, for all positive integers n. Part B, prove the same result for positive values of x using something more advanced, using something called the mean value theorem, which hopefully you've seen before, but if not, I'll quickly go over it as I do the proof. And then part C, we want to graphically interpret this inequality. There's a real nice graphical interpretation of it. All right, part A is an induction proof. So we would want to start by noting that the inequality is true for the base case. First, let x be bigger than -1, and note, the base case is often easy, that when n is 1, we get 1 plus x to the first power is 1 plus x is certainly greater than or equal to itself, which is the same as 1 plus 1 times x. The base case is proved. Therefore, the base case holds, I'll say, or is proved. Next, you have your induction hypothesis. Assume that, let me use a different letter, 1 plus x to the k power, I like to make my k's cursive here, is greater than or equal to 1 plus k times x for some positive integer k, natural number. N stands for the set of natural numbers, which is the same as the positive integers. You don't have to write both of these. To use the principle of mathematical induction, I want to use this assumption to prove that this is true when I replace k with k plus 1. Then 1 plus x to the k plus 1, can I show that that is greater than or equal to 1 plus, in parentheses, k plus 1 times x? You've got to use your induction assumption in some way, or else you wouldn't be doing induction. And hopefully it's pretty clear that you want to write 1 plus x to the k plus 1 as 1 plus x times 1 plus x to the k, because that allows you to now use your induction assumption. This will be greater than or equal to 1 plus x times 1 plus kx. By that induction assumption, induction hypothesis. Now expand this out. This is the same as 1 plus, let's see, outside times outside is kx, inside times inside is x. This is the same as k plus 1x plus kx squared. Be nice to get rid of that kx squared. How can I do so? I can note that, well, k is a positive integer, so it's positive, and x squared is not negative. This is certainly greater than or equal to 1 plus k plus 1x. I can just get rid of that k times x squared and write that, and that's it. Therefore, in the last video I wrote out, by the principle of mathematical induction, it follows that this is true, in this case, for all positive integers, and I will not bother writing by the principle of mathematical induction. I will just write the conclusion. 1 plus x to the positive n power there, n is positive. It's positive integer, is greater than or equal to 1 plus n times x for all positive integers n. X was assumed to be bigger than -1. I'll just add that as a comment there. Done with the proof, QED. Okay, so there's an induction proof, part A. What about part B? Prove the same result for positive values of x by using the mean value theorem. So I'm going to let x be positive, and I'm going to define a function here, f of t. I could use an x, but I'm thinking of x as being a fixed positive number here. Be the function 1 plus t to the n. Okay, this is the function that I'm going to apply the mean value theorem to on the interval from 0 to x, where x is some fixed positive number. In order to apply the mean value theorem, we need to note n is a positive integer here, there's no problem. This function is continuous and differentiable everywhere. Note that f is continuous and differentiable for all t, I could say, or I could say on the entire real number line. Okay, so there's no problem with continuity and differentiability. Of course, again, in using this mean value theorem, I'm using something that would come in a later chapter of a real analysis book. It would not be in chapter 1. It might be in chapter 3 or 4, some chapter where you talk about derivatives and differentiability. And you would also talk about continuity before this point. So I'm using something more advanced than you would get in chapter 1 of your real analysis book, but I think it's worth doing here to show you can prove the inequality this way. N is a positive integer. I didn't write that here, but that's the assumption. Maybe I should write it here. N is a positive integer, a natural number. Note that f is continuous and differentiable on R. Therefore, by the mean value theorem, which I will just abbreviate MVT, it's often called the most valuable theorem. I'm trying to do a chant there for MVT. But here it stands for mean value theorem. By the mean value theorem, there exists, backwards capital E means there exists a number, call it C, between 0 and x. I'm applying the mean value theorem to the function on the interval from 0 to x, such that, well, it's typically written as f prime of c. The derivative of f at c is f of the right endpoint x minus f of the left endpoint 0 divided by x minus 0 divided by the right endpoint minus the left endpoint. And this simplifies to, you're assuming you know the derivative of this would be n times 1 plus t to the n minus 1. Replace the t with c. And f of 0 is 1. And here we have x minus 0, which is x. F of x is 1 plus x to the n. F of 0 again is 1. We get this. What am I trying to show? I'm trying to show an inequality about 1 plus x to the n. Maybe I should solve this equation for 1 plus x to the n. So multiply both sides by x, which is positive. There's no problem with dividing by 0 here. So I get, and then I'm going to add 1. So I'm going to get 1 plus x to the n equals 1 plus n times 1 plus c to the n minus 1 times x. I'm almost done. C is bigger than 0 because it's in the interval from 0 to x because x was positive. Therefore, 1 plus c is bigger than 1. And 1 plus c to the n minus 1 power, including the case where n would be 1, is bigger than 1. Therefore, 1 plus n times this times x is bigger than 1 plus n times x. So there I proved the inequality I wanted. I can write greater than or equal to as well, or greater than, it doesn't matter. I proved the inequality that I wanted by using the mean value theorem. There's another proof. Part C, graphically interpret this inequality, is what part C says to do. Think about it in terms of the function. This function here. Graph that function. When the input is bigger than -1, n is a positive integer here, 1, 2, 3, 4, 5, 6, etc. In the case where n is 1, it would be a graph that would be a straight line with a slope of 1. In general, when n is bigger than 1, like 2, 3, 4, 5, 6, etc., the graph will look like this. Let's go ahead and call the variable x here. So this is the graph of f of x equals 1 plus x to the n. That is greater than or equal to 1 plus n times x, and the graph of that is going to be a straight line with the same y-intercept, the same vertical intercept, and a slope of n. The graph will look like this. This will be the graph of y equals 1 plus n times x. So this function has a graph that's always above the other one, touching at the same point here, the y-intercept of 1 for both of them, but in general, we have the inequality 1 plus x to the n is greater than or equal to 1 plus n times x, when n is a positive integer and x is bigger than -1.